Need a simple intro to UDS, Unified Diagnostic Services? In this practical tutorial, we introduce the UDS basics with focus on UDS on CAN bus and diagnostics over CAN. We also introduce the ISO TP protocol and explain the difference between UDS, OBD2, WWH-OBD, and OBDonUDS. Finally, we explain how to request, record, and decode UDS messages, with practical examples for logging EV state of charge and the vehicle identification number. Unified Diagnostic Services, UDS, is a communication protocol used in automotive electronic control units, ECUs, to enable diagnostics, firmware updates, routine testing, and more. The UDS protocol, ISO 14229, is standardized across both manufacturers and standards, such as CAN KWP 2000, Ethernet, LIN. Further, UDS is today used in ECUs across all Tier 1 original equipment manufacturers. In practice, UDS communication is performed in a client-server relationship, with the client being a tester tool and the server being a vehicle ECU. For example, you can connect a CAN bus interface to the OBD2 connector for a car and send UDS requests into the vehicle. Assuming the targeted ECU supports UDS services, it will respond accordingly. In turn, this enables various use cases: read or clear diagnostic trouble codes, DTC, for troubleshooting vehicle issues; extract parameter data values such as temperatures, state of charge, VIN, etc. Initiate diagnostic sessions to, in example, test safety-critical features. Modify ECU behavior via resets, firmware flashing, and settings modification. Note that UDS and CAN ISO TP are complex topics. As motivation, we've done a case study to show how it can be useful in practice. Specifically, we use a CANedge 2 to request data on state of charge and battery temperatures from a Nissan Leaf electric vehicle. In the example, we also add a CANmod GPS and CANmod temp to add GNSS IMU and temperature data. The multi-frame ISO TP responses and CANmod signals are DBC decoded via our Python API and written to a database for visualization in Grafana dashboards. To check out the case study and the dashboard playground, see the link in the description. Next, let's look at the UDS message structure. UDS is a request-based protocol. In the illustration, we've outlined an example of an UDS request frame using CAN bus as basis. A diagnostic UDS request on CAN contains various fields that we'll briefly detail. First, we have the protocol control information, or PCI. The PCI field is not per se related to the UDS request itself, but is required for diagnostic UDS request made on CAN bus. In short, the PCI field can be 1 to 3 bytes long and contains information related to the transmission of messages that do not fit within a single CAN frame. We will detail this more in the section on the CAN bus transport protocol, ISO TP. Second, we have the UDS service ID or SID. The use cases outlined relate to different UDS services. When you wish to utilize a specific UDS service, the UDS request message should contain the UDS service identifier in the data payload. Note that the identifiers are split between request SIDs, in example 22, and response SIDs 62. As in OBD2, the response SIDs generally add 40 to the request SIDs. We will mainly focus on UDS service 22 in this intro, which is used to read data like speed, state of charge, temperature, and the vehicle identification number from an ECU. See also our full intro article for details on the UDS SID versus other diagnostic services, as well as details on how UDS security is achieved via session control and authentication. Third, we have the UDS sub-function byte. The sub-function byte is used in some UDS request frames. Note, however, that in some UDS services like 22, the sub-function byte is not used. Generally, when a request is sent to an ECU, the ECU may respond positively or negatively. In case the response is positive, the tester may want to suppress the response, as it may be irrelevant. This is done by setting the first bit to 1 in the subfunction byte. Negative responses cannot be suppressed. The remaining 7 bits can be used to define up to 128 subfunction values. For example, when reading DTC information via SID19, read diagnostic information, the subfunction can be used to control the report type. Fourth, we have the UDS request data parameters, including the data identifier, or DID. In most UDS request services, various types of request data parameters are used to provide further configuration of a request beyond the SID and optional subfunction byte. See our article for 2 examples focused on services 19 and 22. We have now gone through the main aspects of the UDS request frame. Let's look briefly at the response. When an ECU responds positively to a UDS request, the response frame is structured with similar elements as the request frame. For example, a positive response to a Service 22 request will contain the response SID 62, corresponding to 22 plus 40, and the 2-byte DID followed by the actual data payload for the requested DID. Generally, the structure of a positive UDS response message depends on the service. However, in some cases, an ECU may provide a negative response to a UDS request, for example, if the service is not supported. We provide a detailed example in our article. To better understand UDS, we will look at how it relates to CAN bus and the OSI model. As explained in our CAN bus tutorial, the controller area network serves as a basis for communication. Specifically, CAN is described by a data link layer and physical layer in the OSI model as per ISO 11898. In contrast to CAN, UDS, aka ISO 14229, is a higher layer protocol and utilizes both the session layer and the application layer in the OSI model as illustrated. Note also that UDS is not limited to using CAN bus as the basis, but can also be used on FlexRay, IP, K-line, and LIN bus. Overall, UDS refers to a large number of standards and concepts, meaning it can be a bit overwhelming. To give you an overview, we provide a high-level explanation of the most relevant ones in our intro article. Next, we'll look more into the transport and network layers, specifically with focus on ISO 15765-2, aka the CAN transport protocol. When implementing diagnostics on CAN, one challenge is the size of the CAN frame payload. For classical CAN frames, this is limited to 8 bytes. And for CANFD, the payload is limited to 64 bytes. Vehicle diagnostics often involve communication of far larger payloads. Here, ISO 15765-2 was specifically established to solve the challenge of large payloads for CAN-based vehicle diagnostics. The standard specifies a transport protocol and network layer services for use in CAN-based vehicle networks. The most common use cases include UDS, OBD, and worldwide harmonized OBD. The ISO TP standard outlines how to communicate CAN data payloads up to 4,095 bytes through segmentation, flow control, and reassembly. ISO TP defines specific CAN frames for enabling this communication as illustrated. Here, the flow control frame is used to configure the subsequent communication. It can be constructed as illustrated. In the simplest case, the flow control payload can set the first byte to 30 and the rest to 0, which will trigger all remaining frames to be sent without delay. Next, let's look at how the ISO TP protocol works for single-frame and multi-frame communication. In vehicle diagnostics, communication is initiated by a tester tool sending a request. This request frame is a single frame. In the simplest case, a tester tool sends a single frame to request data from an ECU. If the response can be contained in a 7-byte payload, the ECU provides a single frame response. However, when the payload exceeds 7 bytes, it needs to be split across multiple CAN frames. Here, as before, a tester starts by sending a single frame request to an ECU. However, in this case, the response exceeds 7 bytes. Because of this, the ECU sends a first frame that contains information on the total packet length, 8 to 4,095 bytes, as well as the initial chunk of data. When the tester receives the first frame, it will send a flow control frame, which tells the ECU how the rest of the data transfer should be transmitted. Following this, the ECU will send consecutive frames that contain the remaining data payload. ISO-TP plays an important role in most CAN-based diagnostic protocols. Before we show practical examples of such communication flows, it is useful to get an overview of the most common vehicle diagnostic protocols. Specifically, a common question is how UDS relates to onboard diagnostics, aka OBD2, worldwide harmonized OBD, aka WWH-OBD, and OBDonUDS. To understand this, it is important to first note the following. OBD is today implemented in different ways across countries and vehicles. This is illustrated via the OSI model comprising CAN-based vehicle diagnostic protocols in use today. Let's look at each diagnostic protocol. ISO-OBD, or EOBD, refers to the OBD protocol specification legislated for use in EU cars, while SEE-OBD refers to the OBD protocol specification legislated for use in US. The two are technically equivalent, and hence often referred to simply as OBD or OBD2. HD-OBD, or SAE J1939, typically refers to heavy-duty OBD and is commonly implemented through the J1939 protocol in both US and EU-produced vehicles with J1939-73 specifying diagnostic messages. UDS, aka ISO 14229, has been implemented by vehicle manufacturers to serve the need for richer diagnostics data and functionality, beyond the limits of the emissions-focused OBD protocols. It is implemented in most ECUs today across markets and vehicle types, though in itself, UDS does not offer the necessary standardization required to serve as an alternative to OBD. WWH-OBD, and/or possibly OBDonUDS, provide an updated version of OBD2 for emissions-related diagnostics based on UDS. To understand UDS, it is useful to better understand WWH-OBD and OBDonUDS. First, let's look at WWH-OBD. WWH-OBD is a global standard for vehicle diagnostics developed by the UN under the Global Technical Regulations (GTR) mandate. It aims to provide a single, future-proof alternative to the existing OBD protocols like ISO-OBD, SAE-OBD, and HD-OBD. Further, WWH-OBD is based on UDS in order to suit the enhanced diagnostics functionality already deployed by most automotive OEMs today. Moving from OBD2 to WWH-OBD will involve a number of benefits, primarily derived from using the UDS protocol as the basis, including an increase in data and DTC richness. For details on the rollout status, see our intro article. Second, let's look at OBDonUDS. Similar to how OBD2 has been split into SAE-OBD, aka SAE J1979 for US, and ISO-OBD, ISO 15031 for EU, the next generation of OBD2 may again be regionally split. Specifically, WWH-OBD has been adopted in EU for heavy-duty vehicles already, but not yet in the US. Instead, the US recently decided to adopt OBDonUDS in US vehicles in the form of SAE J1979-2 standard, which serves as an update to SAE J1979. This is also referred to as OBDonUDS. The aim is to initiate a transition phase starting in 2023 where ECUs are allowed to support either OBD2 or OBDonUDS. From 2027, OBDonUDS will be a mandatory requirement for all vehicles produced in the US. To recap, WWH-OBD and OBDonUDS both serve as possible solutions for creating a next-generation protocol for emissions-related onboard diagnostics. It remains to be seen if the two will exist in parallel, like ISO and SAE-OBD, or if one of the protocols will become the de facto standard across both US, EU, and beyond. In either case, the basis for emissions-related diagnostics will be UDS, which will serve to simplify ECU programming as the emissions-related diagnostics can increasingly be implemented within the same UDS-based structure. as the manufacturer-specific enhanced diagnostics. Alright, so we've now gone through the basics of UDS and the CAN-based transport protocol. With this in place, we can provide some concrete guidance on how you can work with UDS data in practice. In particular, we will focus on how UDS can be used to log various data parameters, like state of charge in electric vehicles. To exemplify this, we will take outset in the CANedge CAN bus data logger. The CANedge can be configured to request UDS data. Effectively, the device can be configured to transmit up to 64 custom CAN frames as periodic or single shot frames. You can configure the CAN ID, CAN data payload, period time, and delay of each frame. To enable single frame UDS communication, you thus simply configure the CANedge with a request frame, which will trigger a single response frame from the ECU, similar to how OBD2 communication can be set up. Similarly, for multi-frame communication, you can configure the CANedge with a request frame. In this case, however, you also need to add the flow control frame as a separate frame to be transmitted X milliseconds after the request frame. By adjusting the timing, you can set this up so that the flow control is sent after the ECU has sent the first frame response. With this setup, the CANedge will record the UDS response data as raw CAN frames. You can then process and decode this data via your preferred software, for example, vector tools, or use our CAN bus Python API to reassemble and DBC decode the frames. For other frequently asked questions on UDS data logging, see our intro article. Next, we'll look at 3 examples of UDS communication flows. To show how UDS works in practice, we'll start with a basic example. As outlined before, WWH-OBD is based on UDS and is mandated in all EU trucks after 2014. As part of this, many EU heavy-duty trucks will let you request parameters like speed, RPM, fuel level, etc. in a way similar to how you'd request this information via OBD2 PID request in a car. See our OBD2 intro and OBD2 data logger intro for details. However, under WWH-OBD, the OBD2 PIDs are replaced by the WWH-OBD2 DIDs. For Service 1, WWH-OBD PIDs are equivalent to the OBD2 PIDs, except that F4 is added in front. To request WWH-OBD vehicle speed, we will use the UDS service 22, read data by identifier, and the data identifier F40D, resulting in the illustrated communication flow. Note in particular how the request is sent with the CAN ID 18DB33F1. This is the same 29-bit CAN ID that would be used to perform a functionally addressed OBD2 PID request in heavy-duty vehicles and can be compared to the 11-bit 7DF CAN ID used for OBD2 requests in cars. The response has CAN ID 18DAF100, which is an example of a physical response ID. Again, matching the IDs you'd see in regular OBD2 responses for heavy-duty vehicles. For a detailed breakdown of the communication flow, see our intro articles. As a second example, let's illustrate how multi-frame UDS communication works in the context of CAN ISOTP. Specifically, we will use the CANedge and the UDS SID 22, aka read data by identifier, to request the current value of state of charge from a Hyundai Kona electric vehicle. To achieve this, the CANedge is configured to send 2 CAN frames. First, a single frame request every 5 seconds with a delay of 0 milliseconds. Second, a flow control frame every 5 seconds with a delay of 100 milliseconds. A subset of the resulting communication flow looks as illustrated. Note here that the initial single frame, SF, request is constructed via the same logic as in our previous example containing the PCI field, the SID22, and the DID. In this case, we will use the DID 0101. In response to the initial request, the targeted ECU sends a first frame response. This contains the frame type in the initial 4 bits, followed by the data payload size in the next 12 bits. The third byte contains the response SID, and the fourth to fifth byte contains the DID. The remaining bytes contain the initial data payload. The first frame is followed by a flow control frame, and subsequently the remaining consecutive frames. These frames contain the frame type in the initial 4 bits, followed by the index counter in the next 4 bits. which in this case is incremented from 1 to 8. The remaining 7 bytes contain the data payload for the DID. We've now shown how you can request and record a multi-frame UDS response to collect proprietary ECU sensor data. In order to extract physical values like state of charge, you need to know how to interpret the response CAN frames. This decoding information is typically proprietary and only known to the OEM. However, in the specific case of the Hyundai Kona EV, we know the following about the SoC signal from online resources. The signal is in the 8th byte of the data payload and is unsigned. Further, the signal has a scale factor of 0.5, a 0 offset, and the unit is percentage. So how do we use this knowledge to decode the signal? First, we need to reassemble the segmented CAN frames. The result of this is shown in the previous communication example. Via reassembly, we can get the CAN frame with ID 7EC and a payload exceeding 8 bytes. The payload in this case contains the SID in the first byte and DID in the second and third bytes. You could process the reassembled CAN frame manually in example Excel. However, we generally recommend to use CAN database's DBC files to store decoding rules. In this particular case, you can treat the reassembled CAN frame as a case of extended multiplexing. We provide an example UDS DBC file for the Hyundai Kona, including the state of charge and temperature signals, which can serve as a starting point. Our CAN bus Python API enables reassembly and DBC decoding of multi-frame UDS responses. See our API examples repository for more details, including the Hyundai Kona sample data. As a final example, we'll look at the vehicle identification number. The vehicle identification number, aka VIN, chassis number, or frame number, is a unique identifier code used for road vehicles. The number has been standardized and legally required since the 1980s. A VIN consists of 17 ASCII characters and can be extracted on request from a vehicle. This is useful in example data logging or telematics use cases where a unique identifier is required for association with example CAN bus log files. CAN data bytes can be converted from hex to ASCII via tables, online hex to ASCII converters, Python packages, etc. Since a VIN is 17 bytes long, it does not fit into a single CAN frame, but has to be extracted via multi-frame diagnostic request response, as in the previous example. Further, the VIN is extracted differently depending on the protocol used. To extract the vehicle identification number from example a passenger car using OBD2 requests, you use service 09 and the PID 02. The logic of the frame structure is identical to the Hyundai Kona example, with the tester tool sending a single frame request with the PCI field 02, request service identifier 09, and data identifier 02. The vehicle responds with a first frame containing the PCI, payload length, response SID, and data identifier 02. Following the data identifier is the byte 01, which is the number of data items, NODI, in this case 1. The remaining 17 bytes equal the VIN and can be translated from hex to ASCII via the methods previously discussed. See also our intro for examples of extracting the VIN via UDS or WWH-OBD requests. Finally, let's look at some examples of use cases for recording UDS data. One such example is UDS telematics for OEM prototype vehicles. As an OEM, you may need to get data on various sensor parameters from prototype EVs while they are operating in the field. Here, the CANedge 2 can be deployed to request data on example, state of charge, and more by transmitting UDS request frames and flow control frames periodically. The data can optionally be combined with GNSS IMU data from a CANmod GPS and sent to your own cloud server for analysis via vector tools, Python, or MATLAB. Other examples could involve training a predictive maintenance model. Specifically, if you're looking to implement predictive maintenance across fleets of heavy-duty vehicles, the first step is typically to train your model. This requires large amounts of training data to be collected, including both sensor data like speed, RPM, throttle position, tire pressure, etc., and classification results like fault or no fault. One way to obtain the latter is by periodically requesting diagnostic trouble codes from the vehicle, providing you with log files that combine both types of data over time. You can use the CANedge 1 to collect this data offline onto SD cards, or the CANedge 2 to automatically offload the data, for example, when the vehicle is returned to stationary Wi-Fi routers in garages. For more on UDS, see our online intro and check out our free sample beta. We also recommend checking out our other simple tutorials, including our intros to CAN bus, OBD2, CAN open, CAN FD, LIN bus, and more. If you liked this video, please share and subscribe. And if you have questions, contact us.